Welcome to our latest video on the topic of Friedel-Crafts Alkylation. This video is suitable for A-level students. By the end of this video lesson, you should understand that Friedel-Crafts alkylation reactions of benzene are examples of electrophilic substitution and are used to substitute an alkyl group onto a benzene ring. You should also be able to write chemical equations and draw reaction mechanisms to describe the Friedel-Crafts alkylation reactions of benzene and its derivatives. And finally, you should be able to explain the problems associated with carrying out this type of reaction. Now, in our previous video, we looked at examples of aromatic electrophilic substitution reactions. And we discussed nitration reactions of benzene and also halogenation reactions of benzene. Now, in the halogenation of benzene, benzene is reacted with chlorine or bromine in the presence of a catalyst such as anhydrous aluminium chloride or iron bromide in the case of bromine and benzene, and a substitution reaction takes place where a hydrogen on the benzene ring swaps with a halogen atom. And if we look at the equation here, we have benzene plus chlorine makes chlorobenzene and hydrogen chloride, and a chlorine atom has swapped with a hydrogen on the benzene ring, and an electrophilic substitution reaction has taken place. Now, the catalyst is responsible for speeding up the reaction by making the electrophile. And in the case of this reaction here, where benzene reacts with chlorine to form chlorobenzene and hydrogen chloride, the electrophile is Cl+, and it's the aluminium chloride or the iron 3 chloride that is responsible for making the electrophile. Now, in our previous video, we looked in detail at the mechanism of electrophilic substitution reactions. And there are usually three main parts to the mechanisms of these reactions. The first step or stage is the preparation of the electrophile. And in this part of the mechanism, the catalyst is heavily involved in making this electron pair acceptor. Now, in the second step or stage, we have electrophilic attack. And this is the main part of the mechanism and involves a pair of pi electrons being attracted to the electrophile and forming a coordinate bond. Now, remember from our previous video on the structure of benzene that benzene has a delocalized ring of pi electrons caused by p orbitals overlapping above and below the ring, and there are 6 pi electrons in this delocalized ring of electrons, and a pair of these electrons are attracted to an electron pair acceptor to form the coordinate bond. Now, the last stage or step in this mechanism is the regeneration of the catalyst. The catalyst in these reactions is able to reform, which means that the reaction can go on and on. Now, in this lesson, we're going to look at another example of electrophilic substitution, Friedel-Crafts Alkylation. And to help us understand this, let's first recap the mechanism for the chlorination of benzene. So now let's look closely at the mechanism for the chlorination of benzene. So the first stage is the preparation of the electrophile. So I'm going to draw Cl2, a chlorine molecule, and then I'm going to draw my catalyst, which is aluminium chloride. And aluminium chloride is electron deficient. It's able to accept a pair of electrons. And I'm going to break the chlorine-chlorine bond here, and both electrons are going to go to the AlCl3. Now, a dative bond is going to form between one of the chlorines and the AlCl3 to produce AlCl4- and Cl+. I've generated my electrophile, and once again, just like in the first example, the catalyst is involved in making the electrophile. It speeds up the reaction and makes the electrophile. Now, stage 2 is electrophilic attack. So I'm going to draw in my electrophile, Cl+, and a pair of electrons from the benzene ring moves towards the Cl plus and forms a dative coordinate bond. So I'm going to draw my intermediate, which will have a positive charge, and I'm going to have a broken delocalized system of electrons, a broken ring of electrons. I'm going to represent this by a dashed line that covers 5 of the carbons. Now, the chlorine joins to the ring before the hydrogen has left, and this is my intermediate. Now this intermediate, this Welland intermediate, is unstable because it wants to have its usual 6 pi electrons. So when the hydrogen is lost from this intermediate, both of its electrons go into the ring and the stable delocalized system of electrons is restored. So the products from stage 2 are chlorobenzene and H+. Now my last stage is regeneration of the catalyst. So the H+ that was formed from stage 2 joins with the AlCl4- that was formed in stage 1, and I'm going to end up with AlCl3, my catalyst has been regenerated, and HCl. Now if we look back at the original chemical equation, we had benzene reacting with chlorine to form chlorobenzene and hydrogen chloride gas. Now this mechanism explains how we end up with these products, because in stage 1, step 1, I have Cl plus and AlCl4- being formed. The Cl plus is the electrophile that we need for stage 2. The AlCl4- is used in stage 3 to regenerate the catalyst. The products of stage 2 are chlorobenzene and H+, and the chlorobenzene is one of my main products in this reaction. The H+ is used to regenerate the catalyst along with AlCl4-. Now for the rest of this video we're going to look at the Friedel-Crafts reaction, which is one of the most important reactions in organic chemistry, and it's named after the 2 chemists who invented this reaction. That is Charles Friedel, a French chemist, and James Crafts, American chemist. And alkylation means substituting an alkyl group into something such as a benzene ring, and a hydrogen on the ring is replaced by a group like methyl or ethyl, and so on. Now to carry out this reaction, benzene is treated with a halogenoalkane. So for example, benzene could be treated with a chloroalkane such as chloromethane or chloroethane in the presence of a catalyst such as anhydrous aluminium chloride. And once again, the catalyst is responsible for making the electrophile, which speeds up the reaction, and the reaction is an example of an electrophilic substitution reaction. Now if we look at the equation here, we have chloromethane plus benzene goes to methylbenzene and hydrogen chloride. Now the halogenoalkane and benzene would be refluxed with aluminium chloride dissolved in dry ether, a non-aqueous solvent, because it has to be anhydrous aluminium chloride, because aluminium chloride reacts violently with water. Now in this equation here, the methyl group, the CH3 group, swaps with a hydrogen on the benzene ring, and we end up with methylbenzene and hydrogen chloride. And the reaction is a substitution reaction, because in a substitution reaction the reactant atoms swap to form products, and that's what's happened here. A hydrogen on the benzene ring has swapped with a CH3 from the chloromethane, and it's an electrophilic substitution because when we look at the mechanism, a pair of pi electrons will move from the ring and form a coordinate bond to an electrophile, an electron pair acceptor. Now it's important to mention that this reaction works with bromoalkanes as well as chloroalkanes, and if I was going to carry out the experiment with a bromoalkane, I would probably use FeBr3 as my Friedel-Crafts catalyst in this case. Now, if I wanted to make ethyl benzene, I would use chloroethane instead of chloromethane. And in the reaction I've drawn out here, the electrophile is CH3+. However, if I was making ethyl benzene, the electrophile would be C2H5+. And if I was making propyl benzene, the electrophile would be C3H7+. Now in the WJC syllabus, Friedel-Crafts reactions are confined to alkylation reactions, where we substitute an alkyl group into the benzene ring. However, other A-level syllabuses will discuss acylation, where an RC double bond O is substituted into the ring. So now let's look at the mechanism for the reaction of chloromethane and benzene. So first of all, I'm going to draw chloromethane, and I'm going to draw the catalyst AlCl3. Now the first step in any electrophilic substitution reaction is the preparation of the electrophile. So the first step is the bond between the CH3 and the chlorine breaking in chloromethane, and a pair of electrons bonds to the aluminium chloride. So a dative bond, a coordinate bond, is going to form between the chlorine from the CH3Cl and the aluminium chloride, and my two products are going to be CH3+ and AlCl4-. Now in step 2, a pair of electrons moves out of the benzene ring. So these are a pair of pi electrons, and these electrons are attracted to the electrophile, the CH3+. And I then have an intermediate where the CH3 and the hydrogen are joined on together, because remember, the CH3 is ultimately going to replace the hydrogen, but in this intermediate the CH3 joins before the hydrogen leaves, and the ring of delocalized electrons is broken, and therefore I represent this by a dashed line which extends over 5 of the carbons. Now my intermediate has a positive charge because I've combined a benzene ring that had no charge with an electrophile which had a positive charge. Now the next step is for the hydrogen on the intermediate to be lost, and the pair of electrons it was sharing with the carbon go into the benzene ring, and this completes the delocalized ring of electrons. So now that is restored, and we have methyl benzene and H+. Now the last step in this mechanism is the H+ that's formed in step 2 joins with the AlCl4-, which was formed in step 1, to regenerate the catalyst AlCl3 and form hydrogen chloride. So if we look back at our chemical equation, we had chloromethane plus benzene forming methyl benzene and hydrogen chloride. Now the methyl benzene is formed in step 2 in this mechanism. The hydrogen chloride is formed in step 3 in this mechanism, along with the catalyst aluminium chloride, which has been regenerated. Now because my product is methyl benzene, the electrophile is CH3+, and if I was making ethyl benzene, my electrophile would be C2H5+. Now when carrying out Friedel-Crafts alkylations, there are two main problems, and the first problem is that you can have multiple alkyl groups swapping with hydrogens on the ring. Now when you put an alkyl group on a benzene ring, you make it even more attractive to electrophiles, and this is because alkyl groups push electrons onto the ring, and this means it will react more readily with electron deficient species, with electron pair acceptors, and you can get multiple alkyl groups being substituted onto the ring. Now to reduce the chance of this, the halogenoalkane is added slowly to benzene in the catalyst, but there is still a possibility that you can get multiple alkyl groups on the ring. So that is the first problem. Now the second problem is carbocation rearrangement. Now the electrophile is a carbocation, and you would have come across these in AS chemistry when you studied alkenes reacting with hydrogen bromide and hydrogen chloride. Now a primary carbocation is a carbocation where you have one alkyl group attached to the carbon with the positive charge, and you will remember from AS chemistry that a secondary carbocation where you have two alkyl groups attached to a carbon with a positive charge is more stable than a primary carbocation, and therefore it's possible that if the electrophile is a carbocation, it will rearrange to the more stable carbocation. So if you have a primary carbocation, it could rearrange to a secondary carbocation, and therefore you will get unexpected products in this reaction. So the best way to explain this is to look at this example. So if I have benzene reacting with chloropropane, I would expect to get propylbenzene and hydrogen chloride. Now I'd expect to get this because my electrophile would be CH3CH2CH2 plus it'd be a propyl group with a positive charge. Now if you look closely at that electrophile, you'll notice that it's a primary carbocation. There's one alkyl group, CH3CH2, an ethyl group, attached to the carbon with a positive charge. Now primary carbocations are not as stable as secondary carbocations, so that carbocation could rearrange to form the more stable secondary carbocation, which would be a CH3 attached to a C plus and a H attached to another CH3. Now I've drawn this carbocation in red, and the result of this rearrangement would be, instead of getting propylbenzene, I would also get 1-methyl ethylbenzene, which I've drawn in red here. So I would end up with two possible products. And in this example, I actually get more of the compound in red. So this is another problem with Friedel-Crafts alkylation. It's the possibility of rearrangement of the carbocation, meaning I get unexpected products. So now let's test your understanding of what we discussed in this video with some practice questions. So here's our first practice question. Read through the question, pause the video and have a go at parts A and B, and then we'll have a look at part C. And then once you've done part A, B and C, we'll then go through the answers. So here's part C, which is asking you to draw a mechanism for this reaction. So pause the video, have a go at the question, and then we'll go through the answers to parts A, B and C. So now let's go for the answers to part 1A and part 1B. So part A is asking you to write a chemical equation to describe the reaction of chloropentane and benzene. So here's the answer to this question. So we have a benzene ring plus CH3, CH2, 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 CH2Cl. So that's chloropentane, which is C5H11Cl. And that will produce pentyl benzene, which is a benzene ring with a CH2, 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 CH2 and CH3. So once again a benzene ring with C5H11 and HCl, hydrogen chloride gas. Now part 1b is asking you to state the name of a catalyst that can be used in this reaction. So the obvious answer is anhydrous aluminium chloride. If you just put aluminium chloride, you'll get the mark. An alternative to this would be iron 3 chloride, and they'd also accept that. So for question 1c, you've been asked to draw the mechanism for this reaction. So first thing I'm going to write down is C5H11Cl, and the bond between the alkyl group and the chlorine is going to break, and a pair of electrons is going to move towards the aluminium chloride, and I've shown this with a double-headed arrow. Now a dative bond forms between the chlorine and the aluminium chloride. So this coordinate bond, this dative bond, produces AlCl4- and the electrophile C5H11 with a positive charge. Now if you drew a pair of electrons moving from the C5H11Cl towards the aluminium chloride, there's half a mark for that, and there's half a mark for getting the correct products. Now for stage 2, step 2, a pair of electrons moves from the delocalized ring of electrons and attacks the C5H11+, so in other words attacks the electrophile, and there's half a mark for that. And then the intermediate that forms has a broken delocalized ring of electrons, and this is denoted by a dotted line, a dashed line, which extends over 5 of the carbons. The intermediate has a positive charge, and the pentyl group and the hydrogen are joined on to the carbon. So the pentyl group joins before the hydrogen leaves. Now there's 2 marks for drawing this intermediate correctly, with the dashed line denoting the broken delocalized ring of electrons, the positive charge, having the C5H11 and the hydrogen both joined on, and realizing that a hydrogen is lost from this intermediate, so a pair of electrons move into the ring. So there's 2 marks for getting this intermediate correct. Now when the hydrogen is lost from this intermediate, I'm left with pentyl benzene and H+. Correctly identifying that H+ is a product here gets you half a mark. So far 4 marks have been awarded out of the 5, and the 5th mark is awarded if you correctly write the equation to show the regeneration of the catalyst. So AlCl4- plus H+ goes to HCl plus AlCl3, and there's a mark for that. Half a mark for the reactants, half a mark for the products. So now have a go at our second practice question, and this comes in 3 parts, A, B and C. Part A and B are on this slide, and part C is on the next slide. So pause the video, have a go at question 2A and question 2B, and then we'll have a look at question 2C. So here's question 2C. Once again, read through the question, pause the video, have a go at it, and then we'll go through the answers to questions 2A, B and C. So now let's go for the answers to questions 2A, B and C. So for question 2A, you're asked to write a chemical equation to describe the reaction between bromoethane and benzene. So I draw a benzene ring plus bromoethane, which is CH3CH2Br, and that goes to ethyl benzene, which is a benzene ring with a CH2 and a CH3, and HBr. So the ethyl group has swapped with a hydrogen on the benzene ring to produce ethyl benzene and hydrogen bromide. Now there's 1 mark if you wrote that equation correctly. So question 2b is asking you to state the type of reaction mechanism occurring during this reaction, and the reaction type is electrophilic substitution. So there's 1 mark for that. Now for question 2c, the question is asking why when you try to prepare ethyl benzene, you get other products. And one of these products has a molecular formula C10H14. And the question is asking you to suggest a displayed formula for this compound and a reason for how it may be formed. Now, when we discussed the problems with this type of Friedel-Crafts reaction, we discovered that when you put an alkyl group on a benzene ring, you make it more attractive towards electrophiles. Now, this is because alkyl groups push electrons onto benzene rings. And when you have this situation with an alkyl group pushing electrons onto benzene ring, it makes the benzene ring more attractive towards electrophiles, electron pair acceptors, because the ring is more negatively charged. So if you got the idea across that having an alkyl group on a benzene ring makes it more susceptible to electrophilic substitution, more susceptible to electrophilic attack, there's 1 mark. And if you drew a benzene ring with 2 ethyl groups on, and you can put these ethyl groups anywhere, that would get you the 2nd mark. So that's how you would get the 2 marks for this question. Now, having 2 ethyl groups on the benzene ring gives you a molecular formula of C10H14. Now that concludes this video lesson. So by the end of this video lesson, you should be able to understand that Friedel-Crafts alkylation reactions of benzene are examples of electrophilic substitution and are used to substitute an alkyl group onto a benzene ring. You should be able to write chemical equations and draw reaction mechanisms to describe the Friedel-Crafts alkylation reactions of benzene and its derivatives. And finally, you should be able to explain the problems associated with carrying out this type of reaction. So that concludes our video. Please check out our YouTube channel, Dr. O Chemistry, and our Twitter site, which contains lots of chemistry information and links, @RadaChemistry.